Hello, we are going to be covering number 7 on the torque worksheet, so let's get into it. So in this problem, as you can see on the screen, we have a horse leaning against the wall on the right. Total mass of the horse and rider, 500 kilograms or something to that effect, and it says calculate the force of the wall, this guy right here, that's exerted horizontally while using the data in the schematic representation in the situation. For the schematic representation, it just means picture with numbers. That's all it is. I don't know why they have to get super complicated. Then calculate the magnitude and direction of the force on the feet of the horse. This is, of course, a horse. Of course. And what's the minimum coefficient of friction between the hooves and the ground? Note that the force exerted by the wall is horizontal, which of course you can also see up here in the picture. Now, before we actually do this problem, I wanted to address something that's going to help us in your understanding with torque a little bit more by looking back at a previous problem. Hopefully, you did this problem and had no issue with it. Specifically, I'm thinking of this guy right here. Okay. Now, you can see from this, right, that the tension is going to pull in that particular direction. Now, there's a bunch of other forces going on here, but I'm specifically looking at that guy pulling at a little bit of an angle. Pulling this way. Now, more than likely in this particular problem, you would put the fulcrum, let's go ahead and shift where you're looking so that you can see this a little better. My apologies. There we go. Okay. More than likely, you put your fulcrum right here. And if you didn't, no big deal. Just watch what it is that I'm trying to show you. Now, this rope or string is certainly going to pull with a force tension. When we go to try to find torque, okay, we have a generic equation of lever arm times the size of the force times sine theta. And specifically, what I wanted to point out is that the point of the sine theta is because torque is lever arm that is perpendicular to force. Now, when we've been doing this, a lot of our bridges or whatever object have been horizontal. Okay. Now, you could do this, of course, with something being vertical. We haven't done too many problems like that. And there's a handful of problems that you guys have done where the bridge is, in fact, already at a diagonal. I bring this up to then say, if we look at the torque in this particular situation, if I first draw the lever arm, which is the distance from the fulcrum to the force, actually let's highlight it up here so it's a little bit clearer. There you go. From the fulcrum to the force, what you need is these two to be perpendicular. Now the purpose of the sine theta is, if I put parentheses around here, really to get the amount of force, there's my angle, the amount of force that is perpendicular. Okay, or in this case, this would be, this guy right here is, let's move this around, that's Ft, force tension specifically in the Y. How much of these are perpendicular? And you can see if you did trig, if you had Ft, the F in this case, and you wanted this perpendicular side, well, hypotenuse, opposite of the angle, well, that's going to absolutely be F sine theta. F sine theta is the force tension in the Y. Okay? So the purpose of sine theta is to get the amount that's perpendicular. Now, if we scroll back down, let's go ahead back to the setup. Okay, scroll back down to number 7. One thing that this is made difficult by is that this is not obviously a bridge like we're used to. It's not a straight line. Okay, so let's look at another setup a little bit different than this that I think will make this doing this problem very easy once you get it, where it's not a straight line. Imagine, if you will, that I had a wheel, okay? A wheel, okay? Just a circle like this. We got spokes here and whatever, okay? And on this wheel, it's a little bit harder to see. 2 seconds. Let's incorporate some circular motion here. There we are. That's a little better. Anyway. On this wheel, I could apply a force in a whole bunch of directions from a whole bunch of spots. Usually if I want the max torque, of course I know to go to the outside. But I could push the spokes. Okay, I could push the spokes, say, I could push it like this. I could push this spoke straight down. Okay, and then I could push this spoke right over here in this direction. Now, the reason why this is a little bit different than what we're used to is, of course, you're used to a straight line path, and the lever arm falls entirely, particularly along that path. Now, what I'm suggesting to you is this. The lever arm is from the fulcrum to the force. That guy right there. Now, as you look at this setup, with this being the lever arm and this force that I'm pushing on that, okay, you could say, oh, I'll find the angle, which you could, certainly. Or instead, we know that this is the lever arm by definition from the fulcrum to where the force is applied. But what we ultimately need in order to get torque is the lever arm perpendicular to the force. So my point is, I could just measure this distance. Let's go ahead and use a different color. Perfect. This distance right here. Because this right there, that right there is the amount of the lever arm, or I could draw it here if you prefer, the amount of the lever arm that is perpendicular to the force. In which case I would not need to measure an angle, because as you can see right here, it's at a nice 90 degrees. Now I could get into the trig of that, but ultimately we don't need to match the trig. We just need these two to be perpendicular. All right, now let's finish number 7. Let's make note at 6:47 that he's actually starting the original problem. So in this, I'm going to draw an absolutely terrible representation of this particular setup. We've got the horse and the horse's legs, okay, nailing it. You don't have to tell me that. I know that's perfect, okay? And then there's like the tail or whatever, and then we got the wall. I didn't even hit the side of the horse. Do you see that? The wall. And then we got the ground right there. Now the forces that are exerted in the problem, it says force of wall. They draw it like this. You're more than welcome to draw it. And I did not switch back. My apologies. You should be able to see my terrible horse drawing that I was just making fun of myself. And what I was just saying is that, hey, they usually draw force of wall, or they not usually. They did draw the force of wall like this. You can move that if it helps you and draw it, say, it's a different color so it's more obvious. You could draw it right here. The main problem with drawing the force of the wall right there is I think it's probably going to, let me check my setup here. It's going to interfere with the center of gravity here just a little bit, but that's okay. Okay. It then said that the center of mass is about here. And that's going that way. And of course, they use W, which stands for weight, which, if you prefer, is the exact same thing as force of gravity. I like force of gravity here just because it distinguishes between force of gravity and wall, but it's the same thing. Now, this is not, of course, the complete extended force diagram. For starters, there is a force on the feet. Actually, it references this in part B of the problem. It says, what's the force on the feet? Now, we give this another name usually. They want to make sure you understand that. Let's go ahead and put force normal. Or force of ground on feet. Okay, that is specifically the force that they're referencing there. Now, I know that that's got to be there for two reasons. The most obvious of which is obviously that the horse is running into the ground. Something better be pushing it up. But the second, and this is important, is even in a extended force diagram, if the total net force is 0, which is the case, then we know that the forces up have to balance the forces down. And the forces right, which we see here, have to balance the forces left. So we asked the question, what is applying a force left? Now, I had a couple of students do this in class. Would highly suggest you take the less than half a minute to do this. Go over and lean up against the wall and ask yourself the question, what is pushing me back towards the wall? And I think you will very quickly find, and even though I'm giving you the answer right now, please go do it. It'll take you less than 30 seconds. I just want you to experience this stuff. But it's going to be your feet. specifically the friction in your feet. It's going to be pushing this way. I also know that that friction has to be equal to force of wall because forces in the x have to cancel each other out. Now, the first thing that was asked to us in part A is what is the force of the wall right here. So the first thing I need to do is I can go, all right, well, should I sum the forces? Well, the only number that's actually given to us in the problem is the mass of the whole thing is 500 kilograms. So, of course, with that, we can get force of gravity, mg, 500 kilograms times g, or 4,900 newtons. But I only know one possible force out of all four of these. By the way, just real quick, we can easily right now answer B. And I'll show you that in just a minute. But hey, force of gravity has to equal force normal, just the force on the feet. So it's that answer. There you go. But we'll tackle that again in a minute. But I need to get force of the wall, and I only know one other force, which should usually lead you to summing the torques is equal to 0. In order to sum the torques, I have to place a fulcrum first. As both of the two of these forces right here are at the same location, and I don't know either of them, well, I technically actually know one, I just told it to you, but let's go ahead and put our fulcrum right there. Put a giant X right there. Now this is where that first conversation that I had with you came up, about how we construct torque. Torque is the amount of lever arm perpendicular to the force. If I go straight to force of gravity here, the lever arm can be easily drawn from the fulcrum to the force. It's right here, okay? And if I wanted to use that lever arm, A, I would need to know the size of that lever arm, which it doesn't tell me, and B, I would need to know the angle between that lever arm and force gravity, which it does not tell me. But if you look at the schematic drawing, what it does tell you is that the distance from the center of gravity on the ground to where the feet is at is 0.35 meters. Mine is certainly not drawn to scale to the actual picture, as I can see that. It also straight up tells you that the height of center of gravity is 1.4 meters, and that's just extra information. You don't actually need to know that whatsoever. That is not the lever arm part that we need. And by the way, technically, given this information, we could do some quick trig to figure out what the lever arm is, but who the heck cares? Because that number right there, 0.35 meters, is in fact the perpendicular amount of the lever arm I just drew to that particular force. So I'm going to say that the lever arm perpendicular of, let's go lever arm of gravity perpendicular is 0.35 meters. Now I'm going to erase this because the picture is kind of confusing. I'm going to erase this lever arm here as best as I can without messing everything up, and get rid of these numbers for a second so that we can focus in on some others. And now I go, okay, what about force of wall, or the torque specifically of wall? Well, what's the lever arm? The lever arm is the line drawn from the fulcrum to where the force is applied. And again, I don't know what the size of that particular guy is. But what I do know is the problem tells me that the force on there is specifically 1.2 meters above the ground. And that amount right there is, in fact, once again, perpendicular to the wall. So I'm going to call this the lever arm of wall that's perpendicular is 1.2 meters. Now, even though I have four forces in this particular setup, what you're going to see here is that since I put the fulcrum here, I should only have two torques. This guy is making things go clockwise, so it's going to have a negative torque of wall. This is making the whole thing shift counterclockwise, so it would be positive torque of gravity. And as we have two of them, one better be positive and one better be negative, otherwise it would never actually equal 0. Out of this right here, what we can do is say, all right, this is negative lever arm of wall, and I'm just going to put perpendicular. The reason why I'm showing that perpendicular is basically it eliminates my need to write sine in there whatsoever, because I've shown that I know it's perpendicular, times the force of wall, which was what we're trying to find, plus the lever arm of gravity perpendicular times force of gravity equals 0. And if you look carefully across what we have discussed, we know out of those four variables, 3 out of 4 of them, so the rest of this should be pretty simple. Let's move that to the other side by adding, divide the lever arm under, oops, I misspoke. I mean, move that to the other side and divide that underneath back. It's just going to leave us with force of gravity perpendicular times force of gravity, sorry, lever arm of gravity, divided by the lever arm of wall perpendicular is going to give us force of wall. And this is 0.35 meters times 4,900 newtons divided by 1.2 meters. Should give us a force of wall of 0.35 times 4,900 divided by 1.2. 1,400, and we'll just go 30 newtons. It's got 29 point some fractions, but that gives me 3 significant figures, so that'll work for what I need. Now, the rest of this, that's the answer to part A. Part B and C, super easy. I've already expressed to you part B a little bit, but here it is in a nutshell. How do I show part B? Sum of forces in the y have to equal 0. Plus force normal minus force gravity equals 0. So force normal equals force gravity, which we already saw equals 4,900 newtons. Done. Next, part C says, what is the minimum coefficient of friction that has to be here in order to get this thing not to move? So part C, how do we get coefficient of friction? It would be force friction divided by force normal. So I already know force normal from the last problem is 4,900. How can I figure out force friction? Well, as already stated, in addition to summing the forces in the y have to equal 0, the sum of forces in the x also have to equal 0. So I'll show that work slightly to the side if you can actually see it. Let's move it just slightly there. Sum of the forces in the x is equal to 0, so positive force of wall because it's going right, minus force friction equals 0, so force of friction equals force of wall, which of course we learned from part A is 1,430 newtons. So the coefficient of friction is going to be 1,430 newtons divided by 4,900 newtons, which gives me 0.29 as a coefficient of friction. Now you might ask why the big to-do about the word minimum. That is because we are dealing with static friction here. And you'll remember that usually with static friction, this number is associated with the maximum, which we don't know that they're actually at. We don't know that the horse, we don't know that the horse is about to slip. So what we know is that friction is the necessary right now is about 1,430 newtons. If the actual coefficient of friction is higher than that, then it could, of course, give us more possibility of friction pushing back in that particular circumstances, which is usually the case. Most things don't hang up against a wall about ready to slip and let their feet fall out from under them. By the way, if they did slip, then friction would go away, and what you're going to see here is the whole thing is going to rotate this way, which is exactly what you would expect if you slipped against the wall. Your feet would fall out from under you, and you would go rotate in that particular direction. Any other questions? Please let me know. But that's how you do number 7.